Okay, let's get started for the parallel resonant converters, DC to DC. Why we call it parallel resonant converter? Because the whole rectifier circuit is in parallel with the resonant tank. Okay, that's why we call it a parallel resonant converter. So this is number one. Number two, if you look at this figure, you'll find that we have inserted an inductor here for some reason, because the output of the resonant tank is a capacitor. Okay, and this capacitor, as we said in the past, this acts as what? As a voltage source. And here we have on the output, on the rectifier side, we have another capacitor. So this also acts as a voltage source. Okay, so this acts as a voltage source, and here this capacitor acts as a voltage source. So we cannot connect two voltage sources together. Okay, we need to have some current source here, which is the inductor, and then connect the output capacitor. Okay, that's why we inserted this inductor in this place. So you'll find that an output inductor is connected to the rectifier output to produce a constant current from the bridge to the load. Since the resonant capacitor is acting as a voltage source, so two voltage sources cannot be connected in parallel. Okay, this circuit can be replaced by a square wave here, source, right? And we have the inductor LR. Okay, we have the capacitor CR, and we have here what? We have a current source, right? This is plus minus I out. Okay, this value I out to be plus minus I out. I will say this is ILR plus minus. Okay, the current that is flowing within the resonant tank, and the current, the output of the resonant tank is equal to Ix. Okay, also can be either positive or negative. The output of this resonant of this rectifier will be I out, and this I out will be same here because this is currents. Let's say this is the average current, so the average will be same, and this will be flowing in the output resistor. Now, if you look at the mode of operations here, you'll find that we have a bit different considerations. You'll find that for mode number one, I will consider that the output current is positive, so this will be always plus I out. Okay, since the output current is positive, okay, so Ix is equal to plus I out, and the voltage VCR is positive. This means what? The diode R1, R2 are conducting. So this is on the output side. On the input side, when the current is positive, okay, so I'll say this ILR is positive, okay, and in this case, switch 1 is on if VAB is positive, if VAB is plus VDC over 2, and diode 2 is on if the input is what? Negative. If VAB is equal to minus V input over 2. So this is for mode number one. So it depends on the current, on the voltage, right? And also on the output side. For mode number two, the same thing here. I will say that the current is negative, so this is minus I out. So Ix is equal to minus I out, and VCR is less than 0. Okay, and in this case, DR3, DR4 are on, conducting, right? And here the same thing, ILR is positive, and when ILR is positive, when the current here is positive, then here we have two options, right? Either the input voltage is positive or negative. Okay, if the input voltage is positive, then switch 1 is conducting. If the input voltage is negative, then diode 2 is conducting. So diode 2 is on when VAB is minus V input over 2. Okay, let's go for mode number 3. We can say that it's clear from the figure here that the current is positive on the output. This is plus I out, and VCR is positive. Diode 1 and diode 2 are conducting. Now I will say that the current is negative, ILR is negative. Then diode 1 is on when VAB is how much? Plus V input over 2. And switch 2 is on when VAB is negative. For mode number 4, you'll find that here the current is negative, minus I out, VCR is negative, diode 3 and diode 4 are on, conducting, rectifier, no problems with this. Now here also the current will be negative, ILR is negative, and in this case also diode 1 is on when VAB is positive, and switch 2 is on when VAB is negative. Now again, let's go and examine the waveforms for this circuit, for this resonant converter. I will say again the current that is lagging, like delayed. Okay, the input voltage is VAB, which is plus VDC over 2, and this is minus VDC over 2. Okay, ILR, the current waveform looks like this. Okay, you'll find that the current is increasing and decreasing this way. You'll find that this is the current inside the inductor. Okay, ILR, the current inside the inductor, but not necessarily the whole resonant current. Okay, because this is not a series resonant converter. Okay, the capacitor and the inductor are not in series. Okay, so this is just can be the behavior of a current within the inductor. The voltage on the output, so this is after the resonant tank, so we expect that there are there are some filter within the resonant tank, so the output should be something similar to the sine wave, right? So this is the output looks like this, VCR. The current across switch 1, it will be this current, okay, this portion, which is the current that was flowing on the inductor, and this is the voltage here, VDC. Again, this is VDC. Here is the current, this portion again is going here. This is for switch 1, okay, for the upper switch. Okay, again here we find that we have hard switching, and here we have soft switching, because here we said switch 1 is on, switch 2 is on, and so on. So when switch 1 is turned on, there is no current, so we expect that the losses is fine, no losses. Okay, when switch 1 turns off, then we expect that we have a current within the switch, so we have hard switching, we have a problem here. Now if you look at the output current Ix, the current that is going to the rectifier, this will be plus minus I out. Okay, this will be plus I out and minus I out, and this should be positive when the output voltage is positive, and negative when the output voltage is negative. Okay, this is the current that is going to the rectifier, okay, to the output circuit rectifier. After the rectifier, the output voltage is just positive. Okay, it's a positive voltage because it's a rectifier, the rectified current, okay, the rectified voltage. But before the rectifier, it will be a square wave. Now again, we can replace the whole rectifier circuit here with an equivalent resistance. Okay, and this equivalent resistance, it depends on the AC voltage and the current. Okay, By the way, the value of this resistance is different from the series resonant converters. For the parallel resonant converters, it's different from the series resonant converters. Now we'll see how it's different. Now let's say again VAB, the input voltage is equal to how much? 4 VDC over pi, right? VDC is how much? VDC over 2, V input over 2. So this will be 4 V input over 2 over pi, okay? And this will be 2 V input over pi, or 2 VDC over pi, right? Now the output voltage, the rectified output voltage is equal to how much? 2 VCR, okay? The first harmonic over pi, okay? And from this we can say that VCR, the first harmonic, is equal to how much? Pi V out over 2, okay? So the output voltage, the rectified output voltage, is equal to VCR, the first harmonic, over pi, and from this we can find the first harmonic, VCR, the first harmonic, okay? Same thing here, ICD, the first harmonic, is equal to how much? 4 I out over pi. Now we said I out plus minus, plus I out minus I out. So the first harmonic is equal to how much? First harmonic, how much? 4 I out over pi. Now simply we can say that the equivalent resistance RE is equal to how much? VCD over ICD, first harmonic, okay? And this is VCR, of course, over ICD, first harmonic. From these two equations that we just obtained here, this will be how much? Pi V out over 2 all over 4I out over pi, and this will be pi squared over 8 times V out over I out. And here, finally, the equivalent resistance is equal to how much? The value V out over I out is how much? This is the output resistance, not the equivalent, the ultimate output resistance, okay? The real one, okay? Not the equivalent one. The equivalent one is equal to how much? Pi squared over 8 times R. So this is pi squared over 8 times R. Now, if you remember, for the series resonant converters, the equivalent resistance is equal to how much? 8 over pi squared times R. But for the parallel resonant converters, pi squared over 8 times R. Okay, they are different, so it depends on the converter. Okay, here of course the values are different because the behavior of the circuit is different. Okay, the values of the current, the rectified current, the rectified voltage are different. Okay, so of course we have different values here. Now let's go back to this circuit here, okay, and try to find the value for the output voltage over the input voltage, so the relation between the output and the input, and see how we can obtain this. If you look at this circuit, you'll find that here we have VCD, okay, VCD, the output, and here we have VAB. So what we need to do is to find VCD, the output voltage, the first harmonic, over the input voltage. Now from the voltage divider, okay, you will find that VCD is equal to how much? The impedance of this network, the resistor and the capacitor, okay, and this is equal to how much? The equivalent, these are in parallel, so this will be 1 over j omega CR, okay, plus 1 over R equivalent. 1 over R equivalent. So this is the equivalent impedance for the capacitor and the capacitor and the resistor on the output. Okay, all of this should be over the same impedance plus the impedance of the reactance of the inductor. Okay, plus J omega LR, right? Now if you remember, we said if this is Rx and this is Ry and this is V input, right? So V out over Vn is equal to how much? Ry over Ry plus Rx, right? Here is the same thing. Okay, just we need to obtain the equivalent of this one. So this is Ry and this is Rx. So this is multiplied by what? VAB1. Okay, now let's simplify this one. VCD1 over VAB1 is equal to how much? Do simplification here. So this is 1 over 1 minus omega squared LRCR squared plus omega LR over equivalent resistance all squared. Now we know the relation between VCD and VAB and V out over Vn. So these we can obtain them from the previous slide. So you'll find that V out over Vn is equal to how much? 4 over pi squared times 1 over the root square of 1 minus omega square LRCR squared plus omega LR over R E squared. And this is the relation between the input voltage and the output voltage for the parallel resonant converters. Try to draw the relation here. So this is V out over Vn. You'll find that here we don't have one peak, okay, because the quality factor, we cannot extract the quality factor from like as a one piece within this equation. You'll find that if we change the quality factor, also the value of the output over Vn will be changed as well. Okay, so here you'll find that, so at some resonant frequency you'll get the peak, but the peak will be changed. Okay, so here we have high Q and here we have small q. Okay, also again we'll make a comparison. Next time we'll make comparison between the all of these converters. We'll draw them on MATLAB with nice figures, but now we have a clear idea about how the parallel resonant converters, how the series resonant converters works. Okay, and also we know some differences between the series and the parallel resonant converters. Now let's jump to one example here. Here we have an example. The example says we have a parallel resonant converter circuit, and this is a DC to DC converter. Okay, has the following parameters. The input voltage is 100 volt. The resonant inductance 8 microhenry, and the resonant capacitor 0.32 microfarads. The load resistance is 10 ohms, and the switching frequency is 120 kilohertz. The question says find the output voltage of the converter. Assume that the output filter components produce a ripple-free output current and voltage. So we assume that there is no ripple on the input, on the output voltage and the current. How to solve this question? This is just a straightforward question. We assume that we operate at the resonant frequency. The current and the voltage are in phase. The values of the capacitor inductors are the resonant values. Okay, so here we need to find the resonant frequency. The resonant frequency is equal to how much? 1 over the root square of LR times CR. Okay, and this is equal to 625 kiloradian per second. Okay, and here we obtained the resonant frequency, which is equal to how much? 99.4718 kilohertz. Okay, now if we use this as a switching frequency, then definitely we are operating at resonance. But here in the question said we are operating at 120 kilohertz. So we expect that we operating at a frequency that is greater than the resonant frequency. So the converter is inductive. Okay, inductive converter, not resonance, inductive. And also the output voltage is not the maximum, is something less than the maximum value. Okay, because if you remember here, this is the maximum, this is F naught, this is 120 kilohertz. Okay, we can find the normalized frequency omega s over omega naught. This is what? 120 over 99, it will be 1.21. So here inductive, as we said, and we know the relation between the input and the output. So V out over Vn is equal to how much? 4 over pi squared times 1 over 1 minus omega squared LRCR square plus omega LR over the equivalent resistance squared. Again, V out over Vn is equal to 4 over pi squared, and this is equal to how much? 1 minus omega squared LRCR squared plus omega LR over the equivalent resistance. The equivalent resistance is equal to how much? RE. RE is equal to pi squared over 8 times R. R is equal to how much from the question? 10 ohms. So R equivalent is equal to 10 times pi squared over 8, right? Just calculate this one. You'll find here we have, it will be 12.34 ohms. This is the equivalent resistance, okay? But the actual resistance is how much? Is 10 ohms, right? Substitute with this value, so you'll find V out over Vn, which is how much? 100 volt, 4 over pi squared. This is 1. We know all information here. 1 minus omega squared, how much? This is 120 kilohertz, right? 2 pi times 120 kilohertz, so this is omega squared. LRCR are given, plus again omega is given, LR over the 12.34 squared. Calculate this, how much you will get the value. Let me calculate it. So here we have 12. So here the output voltage is equal to how much after calculations? This will be 60.66 volt. Okay, so this is the output voltage to operate at the 120 kilohertz. So here, if you try to draw this relationship, you will find that the maximum, V maximum, this is the resonant frequency, which is 99 kilohertz. At 120 kilohertz, this will be 60.6. So absolutely the maximum will be greater than 60 volt. It will be something like 80, 100 or something. You can see these are very simple lectures, not difficult. There are just a few calculations. As long as we understand the whole idea of the resonant converters, so hopefully no problems. I'll stop here for today. I hope that you enjoyed this lecture, and I'll see you next week.